So last section we're going to take a look at is 14 part 2, so a little bit more with graphing. But today we're going to look at what happens when we graph where the degree of the numerator is greater than the degree of the denominator. Yesterday what we did was when the degree of the numerator was smaller. Okay? So we're going to look at graphing rational functions where the degree of the numerator is greater than the degree of the denominator. Ideally, we don't want them to be too much bigger, because the further apart the two degrees are, the worse it gets to graph. Like if the top is a degree 2 and the bottom is a degree 1, that's not bad. If the top was like a degree 5 and the bottom was a degree 2, that's a difference of 3. 5 on the top, 2 on the bottom. That's going to be harder to graph. Okay, so ideally we don't want the degree to be too far apart. So what we're going to look at, and this is something specific to having the degree in the top bigger than the degree in the bottom, is called an end behavior asymptote. It's called an EEBA. So this represents us, having some kind of problem. When we do an example, it'll look like this. So h of x represents a polynomial on the top. G of x represents a polynomial on the bottom. To be a little more specific, the degree on h of x will be larger than the degree on g of x. Just like this first one, degree 3, degree 1. And the way you find the EEBA is the quotient. That's it. The EEBA is the quotient. So we've done that before. How do you get the quotient? You divide the two of them. If you can use synthetic division, that will be easier. If you have to use long division, then we'll do it that way. But the EEBA is just the quotient when you divide that out. So maybe I should say that. Is the quotient of h of x divided by g of x. So there's no new skill to learn to find it. You already know how to do long division. We're just calling the quotient a new name now, calling it an EEBA. EEBA is the quotient. And again, EEBA, I think I already said it, but it stands for end behavior asymptote. Okay, I'm just going to say EEBA from that one. Okay, any question on that? All right, so let's look at this one, and let's try to find the EEBA. All right, let's start by doing the quotient. Is this a problem that I could do synthetic division for, or would I have to do long division? Yeah? I can do synthetic, so let's do that and get the quotient. What number goes on the outside? Tyler? 2. 2? And Matt, can you tell me my numbers on the inside?
You have 2, -4, and 3.
Careful. We missed something. Has to be 4 numbers on the inside here.
Oh, 0 and 3.
Yep, 0 and 3. Okay, so 2, -4, 0, 3. Bring down our 2. Jack, 2 times 2?
4.
4. Casey, what's -4 plus 4? 0. 2 times 0 gives me 0. 0 plus 0 is 0. 2 times 0 is 0. And 3 plus 0 is 3. Okay, so what is my quotient in this case, if we were to write it out? Bailey?
2x squared plus 3.
2x squared. To have a plus 3, you'd have to have a 3 right
Yeah,
there.
no, that's the remainder.
3 is the remainder. So anything else there? Nope, it's 2x squared plus 0x plus 0. But you can just write 2x squared. Okay, so that's my quotient. Now let's talk about that 3. Not that it's really important here for what we're going to do later on, but they did ask about it. What's the remainder in this case? Chris?
3.
It is 3. Again, we're not going to really need that today. And the EBA in this case is what? Yeah,
2x squared.
2x squared. It's the same as the quotient. Now let's think about that a little bit. 2x squared. When you graph something that has a highest exponent of a 2, what shape is that? Yeah.
It's a parabola.
It's a parabola. And this is a parabola that's an asymptote. Okay, so what does that mean? It means you might have something like this. And let's say you had a graph. I'll draw that one in black. Maybe your graph would do something like this. What's happening here is the graph in black is getting closer and closer to something. And usually it gets closer and closer to something that's a straight line, right? Usually we have something like this. Maybe the graph curves down and gets very close to it. Well, this graph is getting closer and closer to something, but it's getting closer to something that curves. That's what's happening here. All right, so we have an asymptote that curves, and our graph gets very close to that curve as we approach infinity. And that's why I said the further apart the degree and the top and the bottom are, the worse it gets. Because this one had a degree 3 in the top, a degree 1 in the bottom. That's a difference of 2. If this was like a degree 8 in the top and a degree 2 in the bottom, that'd be a difference of 6. That'd be a 6th-degree polynomial we could have to sketch, which could be kind of hard. All right, but in general, the hardest one we would probably have is a quadratic, like that. Right? We're going to go through and sketch that a little bit more accurately, but that's the idea. So there's a difference between an EBA and an EBM. They're not the same thing. The EBM is easier to find. It's just the highest degree term in the top divided by the highest degree term in the bottom. The EBA, you have to do long division. That's what we're learning today. Now, when you find an EBM and an EBA, sometimes they're the same, sometimes they're different. Let's go back to the one we just did. And then I'll come right back to this. If you were to find the EBM here, the highest degree term in the top is 2x cubed. The highest degree term in the bottom is x. That's an EBM of 2x squared. Well, that was also the EBA. The only reason the EBM and the EBA came out the same is because both of these were zeros. Right? If this had come out to like a 1 right there, then my EBA would have been 2x squared plus 1. But because those both came out to zeros, that's what made the EBA the same as the EBM. Okay, so just the way the numbers worked out on that one. And for the kind of problems we did yesterday, the degree of the numerator was always smaller or equal to the degree of the denominator. This is not what we're doing today, but it's what we did yesterday. In the kind of problems we did yesterday, your asymptotes are always straight lines. They're always straight lines. You might have some verticals, you might have some horizontals. Well, today, you're still going to have the verticals. Those aren't going away. Okay, you're still going to be finding the roots of the denominator, and those will be my verticals. But if the degree of the numerator is greater than the degree of the denominator, then what can happen is you start to get asymptotes that are curved. You will not have any horizontal asymptotes in the problems today. If the degree of the numerator is bigger than the denominator, you will not have horizontal asymptotes. It has to be smaller or equal to have a horizontal. Right, so we're not going to focus a bunch on the curved asymptotes. We're going to try one that's curved, and then we're going to try one other one that's, I think, a little easier than a curve, but a little harder than what we did yesterday where it's horizontal. You'll see. There is something in between, which we haven't talked about yet. So let's actually take this problem. Let's graph, you can just watch me graph it. I'm going to graph it. So I'm going to type in 2x cubed minus 4x squared plus 3. And if anybody really wants to graph it, I can get you a calculator. But I don't think you need to. And now let's graph the EEBA, 2x squared. So when I hit graph, what should happen is it should look like these two graphs are getting closer and closer as we go towards the right and to the left. Now, I remember from doing this graph that it ends up going down off the standard window, so I am going to fix that. So let's go to my window, and let's try like, actually, does it go up or does it go down? I think it goes, let's try up. Let's set this at 25. So the first one you're going to see is the original. Okay, that's the original. And the next one you're going to see, actually I'll put that before the asymptote gets drawn. And the next one is going to have the asymptote. All right, so let's kind of compare these. So if you look carefully, can everybody see how the red curve, that's my asymptote, and the blue one, how they're getting closer and closer? And if you go to the left too, it almost looks like they get right on top of each other. That's because there's only so many pixels on the screen, and eventually they look really close. But they never actually touch each other. Okay, they just get closer and closer and closer and closer. All right. So the one on the right is what it looks like before you put the asymptote in, and then the one on the left shows the asymptote. So towards the ends, it looks just like a parabola. This part here and this part here. So those two parts would continue on and look like a parabola. But it's in the middle that something weird happens. And that's because, if you look at the original problem, we divided by x minus 2. What value are you not allowed to plug into this? Yep. 2. So what happens at 2 is we get a vertical asymptote. So not only do we have this curved asymptote, we have a vertical. It's like the vertical breaks the parabola. Okay? It basically takes this end that would want to connect up to the other part, it takes it, it breaks it, and it pulls it down. Pulls it down to negative infinity. And then it takes this other part right here that would want to go straight to be able to connect, and it breaks it and it bends it up to positive infinity. So it's like the parabola gets broken in the middle and stretched out in opposite directions. And that's what's happening with the vertical asymptote. All right, so let's take a look at. I just did this for you. We did example 6. It was just a graph and see how the 2x squared looked like an asymptote. So we don't have to do that again. So let's see if we could actually make a sketch of this. Okay, how would you do it by hand? All right, so the first thing you'd want to do is you'd want to look and say, okay, the degree in the top is bigger than the degree in the bottom. That means it's the kind of problem he taught us on Thursday. I have to do the long division and get the EEBA. We've already done it. EEBA is 2x squared. So we want to graph 2x squared. The easiest way to do it is pick some points and make a little table. Okay, if you plug in 0 for x, what does that give you in that formula? Yep.
0.
0. Okay, let's do another. What if you plug in 1 for x? What does it give you? Yeah? 2. What if you plug in -1 for x? 2. How about if you plug in 2? What did you get? Yep. Sarah?
8.
8. How about -2? Tyler?
8.
You also get 8. And I'll do one more. I'll do 3. That would give you 18. And -3 would also be 18. Parabolas are symmetrical. That's why we're getting the same numbers. Okay, so let's graph that, and then we're going to make a dotted line out of it. And that's going to be our asymptote. That's not the graph, just the asymptote. All right, so 0, 0. And notice how my y-axis goes by 2's. Okay, so that I did that so I could get some more space. 1, 2, -1, 2, 2, 8, -2, 8, 3, 18, -3, 18. Okay, and it's easier for me if I scale this down so I can draw it easier. So, let's draw our parabola. I'm going to make that dotted. And that's going to be our asymptote. Okay, so I got that. Now, the next thing we would want to look for is a vertical asymptote. You don't have to look for a horizontal. There isn't one. When the degree in the top is bigger, forget about horizontals. You got to do this curved thing. Okay. All right. What's my vertical asymptote in this case? And how would you write it as an equation? Yeah. X equals 2. If that's a question on the test and you put 2 in the box, and I say write the equation, I wouldn't give you credit if you don't have an equal sign. Equations have to have a letter on the left, an equal sign in the middle, and a number on the right, at least for asymptotes. Okay. All right, so we got the vertical at 2. Let's draw that in. And now we just have to sketch our graph. With a parabolic asymptote, you usually end up sketching in this little section right there. And then the other part of your graph usually ends up in this section over here. That's what usually happens. So all you can do at this point is plot some coordinates and see what you get. All right. Let's pick a number that's near 2. Because that's my vertical asymptote. Somebody give me a number that's just a little bit smaller than 2. Tyler?
1.99.
All right, 1.99. And I'm down at -3,000. Okay, so I'm dropping way down. Now, a little bit bigger than 2, I already have some numbers typed in from the last problem. A little bigger than 2, I'm up at 30,000. So I'm way up. But I would try some other points between 2 and 3 to see what's happening in that section I just circled. So let's try, I would try like maybe 2.5. And we're at 18.5, just barely I can get that on the graph. So 2.5, 18.5 would probably be about right there. Let's try like 2.9. Okay, that's a little bit off my graph, but not bad. It's just above 20. So 2.9 and just above 20. Okay, so I've got 3 points. I can kind of see what's happening. Right, remember, this is my dotted line. That keeps going. And this parabola keeps going as well. And they keep getting further apart. The parabola is going to curve out a little bit, and the vertical line goes straight up. So, in this section, it's going to look something like that. All right, so that's the right part. And now we got to do the left part. Right, you guys tell me, what would be a good value for x to start to get how my graph is going to look in this area? What would be a good x value to check? About that?
0.
Okay, let's check 0. 0, negative 1.5. Okay, so probably, remember I'm going by 2s, so probably about right there. That's good. Can somebody give me another good value to check? Yeah?
Negative 3.
Negative what?
Negative 3.
All right, negative 3. Let's see. I'm at 17.4, so I can just barely get that on the graph. Probably about up there. Okay, someone give me another value I could check. Jack?
Negative 2.
Okay, I can check negative 2. It's not going to tell me too much more. I kind of know what's happening over here. So I'm up at 7.25, maybe about right there. But I need some more values in another area. Tyler?
Probably like 1 again.
Which one?
Like, wait, like 1.
1. Yep, I don't really know what's happening over there. 1, negative 1. All right, so 1, negative 1 puts me there. We know that we're curving down here, so I think I got a good idea what's happening now. All right, let's zoom out a little. The graph is going to stay very close to the parabola. Just go through the points you made. But then it's going to start to kind of get a little bit away from it. It's going to curve through that point, and then it's going to curve back down, staying very close to the asymptote. All right, and if we hit graph, we can see, we already saw it, but we have a pretty good sketch, I think. All right, there you go. There's your graph. So when in doubt, just plot more points. If you need 10 points, plot 10. If you need 15, plot 15. Just use as many as you need. Especially in areas where things start to curve, that's where you need more detail to see what's happening. Okay. I don't really need more detail at negative 2, negative 3, negative 4. I know what's happening. It's just staying next to the asymptote. But when it starts to move away from it, that's when I got to see how it's curving. Okay. All right, any questions on that one? So that's the hard one for today. All right, let's take a look at, let's see, determine the end behavior and sketch a complete graph, and use a calculator to find a complete graph. All right, let's try this one. I thought there was one I had before it, but I guess how we did it. Okay, let's try this. Now, what's the difference between the degree in the top and the degree in the bottom this time? Last time it was a difference of 2, and we had a quadratic. Chris?
Good, difference of 1.
Difference of 1. So this one's going to be a little simpler. It's not actually going to have a parabolic asymptote, but let's see what happens. The degree in the top is bigger, so they are asking me to find the EEBA. Can I do synthetic division on this one?
No.
No. The denominator, that's way too complicated to use the synthetic division the way we know it. So let's put x squared plus 2x minus 3 divided into 2x cubed, 7x squared minus 4. All right. So Casey, what do I get if I divide x squared into 2x cubed? Casey. Hi. What do we get if we divide x squared into 2x cubed? Yeah, if we just put an x here and we multiply it back out, x times x squared doesn't give me 2x cubed. So we're close, but we need something else. Tyler?
Be 2x.
Yeah, it's going to be 2x. Now if we multiply it back out, 2x times x squared is 2x cubed. And then I forgot one thing, but it didn't mess us up yet. Always fill in zeros for any terms you're missing. Again, it didn't mess anything up yet. All right, so now multiply it back out. 2x cubed plus 4x squared. Now it would have messed something up. Minus 6x. And what do I do with these columns? Got to be careful because it's different in synthetic division compared to long division. Jack?
Subtract.
Subtract. 2x cubed minus 2x cubed is gone. 7x squared minus 4x squared is 3x squared. And 0 minus 6 is a plus 6. X. Okay, bring down your next term. Now, once we do the next step, we're done. Unless you want the remainder, but we don't care about the remainder. That's not the EEBA. What do we get when we divide x squared into 3x squared? 3. And you're done. Okay, continuing would only give you the remainder, and that's not part of the process. You only need the quotient. So this is your EEBA. 2x plus 3. What would that look like when you draw it? It's not a horizontal line, but it's not a curve like a parabola either. What is it? Yep. It's like slope-intercept, right? That's a line that's going to be on a diagonal. And that's called a slant asymptote. So it's an asymptote that's on an angle. It doesn't curve, but it's not as simple as being horizontal. It's on a slant. So your y-intercept is at 3. And as Tyler said, it's slope-intercept, so your slope is 2. Rise over run. Up 2, right 1. Up 2, right 1. And you know what I should do? I remember this one. I do need to zoom out a little bit. So before I sketch it, I'm actually going to scale my graph. Okay, let me do that first. So let's make this 0, 2, 4, 6, 8. If you have more room on your paper, you might not have to. But I just remember I need to. Okay. So we're going to go by 2s. So up 3 put a dot there, and then up to over 1. Up to over 1. So up to would bring me 1, 2, over 1. Up to 1, 2, over 1. Okay, and I'm going to do this a few times. Okay, up to over 1, up to over 1, up to over 1, up to over 1. All right, I think we get the idea now. So draw a line through those points. And we'll make it dotted in a second. Okay, that's pretty close enough. All right, so make that dotted. Okay, so there's my slant asymptote. And the other thing we're going to check for is a vertical asymptote. So x squared plus 2x minus 3. Set that equal to 0 and solve. X squared plus 2x minus 3 equals 0. Okay, let's see if we can factor it. Two numbers that multiply to give me 3 are 1 and 3. And we're going to need a minus and a plus. Let's check. X squared plus 3x minus 1x is a plus 2. Negative 1 times 3 is negative 3. Perfect. So, what are my two vertical asymptotes here? Yep.
1 and negative 3.
1 and negative 3. Kind of annoying that we have two of them, because when you have two, it breaks your graph into another section you have to check. Okay, so we're really going to have to check 3 sections, okay, because we're going to have 2 splits. Think about if you take a piece of string and you cut it twice, you're going to get 3 parts. Okay. So I'll just continue this down like that. X equals 1. Okay, we're going to need a line there. Let's go like this. X equals 1 and negative 3. All right, so 1, if I'm going by 2's, would be there. Negative 3, I think would be right there. All right, let's put those dotted. So now I think you can see kind of how it breaks your graph into 3 parts. You're going to end up with something in the left part, something in the right part, and then something in the middle. So we're just going to plot some points and see what we get. Okay, easiest way is to use the table. And those asymptotes will guide us as we put in more points. All right, so 2x cubed plus 7x squared minus 4. And we're going to divide by x squared plus 2x minus 3. Again, this would have been easier if we only had one vertical asymptote. Then it would have just split it into 2 pieces. But the 2 vertical asymptotes splits it into 3. All right, so let's go second table. Okay. And let's pick some values that are just to the left of my first vertical asymptote. What's a value a little bit smaller than negative 3? A little smaller than negative 3, yep. Yeah, negative 3.01. We're up at 1,246, so we're up at infinity. Okay, so just to the left of our first asymptote, way up there. Let's go just to the right. Okay, a little bit bigger than negative 3 would be negative 2.99. We're at negative 1,253. So way down there. Okay, my next vertical asymptote was at 1. So don't plug in 1. You can't do that. You're going to get an error. You just divide it by 0. But let's plug in a number a little smaller than 1. Ethan, can you give me a number a little smaller than 1?
0.009.
Point what?
Oh, 0.999.
Yeah, I would just do like 0.999. And you're at negative 1,245. Okay, so way down. Let's plug in a number a little bigger than 1. 0, 1. We're up at 12,500. So up very high. Okay. Now let's plug in some more x values over in this range and see where my y values are. So let's try 2. 2, 8. Okay, that's a point. So 2, 8. Good. Let's try let's try 10. That's off my graph. Let's try 8. 8, 19. All right, so 8, I'm up at 19, which is about right there. Okay, and I'm going to erase these red dots that I originally used to get my asymptote, just so we don't get confused by them. All right, so I've got 3 dots in that section. I can kind of see what's happening. It's going to come down, stay very close. It's going to go through this point. Oops, messed that up a little bit. It's going to curve. And then it's just going to keep getting closer and closer and closer to that dotted line. Okay, so that's pretty good. Let's, we need a little bit more information in the middle. Let's try 0. 1 1/3. Okay. I think we've got enough there, because if you zoom out, you've got a point down here, another point down here. Maybe you want a little bit more. I mean, it's up to you, but I can kind of see what's happening. It's going to stay very close. It's going to curve, go through that point, and it's going to come back down to get that other point on the way down. So there's your middle. Now we need to just investigate what's happening in this area. Can somebody give me an x value that would tell me what's going on in that area I just circled? Yeah.
-8.
We can try -8. I'm not sure if I'm going to be off the graph. No, I'm not. -8, -13, roughly. So -8. 2, 4, 6, 2, 4, 6, 8, 2, 4, 6, 8, 10. It's hard for me to see it. I think we're down around there. So that's 0, 2, 4, 6, 8, 10, 12, 13. So I think 13 is like right around there, maybe. All right, what's another good one we could try? Yeah.
-4.
Yeah, let's do -4. I have a feeling the further down I go, the more my line is off, because I put all the points up here when I drew it. So if my line was a little bit off, it's going to get worse and worse as I go down to the left. But, it's all right. So -4, -4. Let's see. -2, -4, -2, -4. Right about there. Okay, I think we got enough points. So we've got this point way up here. It's going to come down, stay very close, start to curve a little bit, and then again, stay very close. So that's pretty much what the graph, I think, is going to look like. So we just have to try lots of different x values on our graph and kind of see, and remember, the vertical asymptotes are going to break it into different sections. Let's see how we did. Let's hit graph. Okay, so there's that piece on the left. There's the piece in the middle. And then the piece on the right. Yeah, that's pretty It's pretty good. My window's a little different. I think I only go to -10. I go to -20 on this one. But yeah, that's pretty good. Any questions on that one? Okay, so graph and calculator are very, very helpful to use that table. All right, let's finish up. This is just a graph. I want you to notice what happens when you graph it. And it's just to remind you about something. Let's graph 2x to the 4th plus 7x cubed plus 7x squared. Whoops. Messed that up. 7x cubed plus 7x squared plus 2x. And we're going to divide by x cubed minus x plus 50. All right, let's do zoom 6. So I want to see if I can find a window that shows what this graph really looks like. Okay, so that's what we've got. Let's look at that. And is there anything on that graph that looks a little funny, like you might want to check it out a little closer and see what's really happening there? I would say that's a good window that shows you the big picture. But I think there's something here we may want to check out a little closer and see what's really happening, because I can't tell from that. Zach?
The bottom of the travel.
Yeah, it looks like it's getting really flat. So what I might want to do is, let's set our window to just that red section. Let's do -3 to 1 and -1 to 1. And let's zoom in on it and see what's really happening. -3 to 1 and -1 to 1. All right, so we're just going to focus on that box in red. That's what you're going to see now. So I zoomed in just on that section, but I'm still not really 100% sure what's happening there. Kind of looks like, what does it kind of look like might be happening? We may have to zoom in a little more to see it, yeah?
It's overlapping.
It looks like it's actually going right over the axis and maybe coming back up. Right, so now let's zoom in again. I'm not going to change my x's. I'm going to keep those the same. But let's zoom in 10 times as much on the y-axis. So instead of -1 to 1, let's do -0.1 to 0.1. So now, instead of looking at -1 to 1, I just zoomed in like 10 times as much. So let's hit graph and see what we have now. And I'll put that picture right there. All right. Now I think we can see pretty good what's happening. How many times does it look like that graph crosses the x-axis? Ethan?
4 times.
Yeah, crosses 4 times. So the point here is always make sure you zoom in and look for the detail. Like if I said, how many times is this crossing? And you just look at this, you might say, oh, it doesn't look like it ever crosses. But it actually does cross 4 times. Then you have to zoom in to see it. So sometimes you have to zoom in to see detail. Sometimes you need to zoom back out because something is off the screen. Keep that in mind. Yeah.
Would you put something like this on a test?
I mean, something that uses this concept, yes. The idea of having to adjust a window on a calculator to see details that you can't see on a standard window. Whether that means you need to zoom in or zoom out, definitely. Yeah, you always have to know how to set your window. Okay. All right, any questions on that? All right, so that's the homework for tonight. Okay, on page 235, it's 40, 41, 45 to 47, 51, and 55. Okay, and I can go through a list of things that you should know for the test tomorrow. Okay, give me one second.